I'm Cadet Ansh Mingani.
I'm Cadet Mark McMahon.
Our mission is to identify forest fires in remote locations and alert emergency managers. After analyzing our mission, we decided on our orbital requirements. We decided that the minimum useful amount of data could be collected by 14 passes over the target area. The CubeSat will take 10 square miles of pictures each day. After analyzing different orbits, we decided that we would gather the best data in low Earth orbit. The CubeSat must have a camera resolution of 0.5 megapixels to get accurate images. We determined that the solar panels must generate enough power to charge the battery and/or the Raspberry Pi. To maximize the data collection, the CubeSat should be able to orient itself.
Here's our concept of operations document. In our concept of operations, we have four different phases. The first one being the pre-launch phase, in which the satellite tests all its functions, including the structure of the satellite and other physical things that it cannot test in space by itself. And then once that passes, it goes to the launch and deployment phase. And if that fails, then obviously, it will be a good thing that it failed during the pre-launch phase and not any other phase because we can take it back and fix that. But once it goes to the launch and deployment phase, we are going to change the mode of the satellite so that it can communicate with the ground station so that we have the master control on and we have the communications on so that we can communicate with it. And then once the satellite deploys, we go into the orbit insertion phase, which basically takes the solar panel on the satellite, uses it to find where the sun is, and then uses a reaction wheel to stabilize the rotation of the satellite and point it towards the Earth based on where the sun is. So relative to the sun, where is the Earth? Our satellite calculates that, and then it orients itself towards the Earth. And then we have the start phase, which is the biggest phase of them all because we basically turn all of the satellite on at that point, and we basically turn up all of the systems of the satellite so that it can perform its activities and duties properly. So it goes into an autonomous testing phase in which if one of the subsystems fails, there are contingencies that we have drafted. There are error contingencies on how the satellite would autonomously handle that. And we can also send the satellite commands through a master program here on Earth, and it has a receiver up in space, and it has something that can interpret those commands up in space so that it can execute what we tell it to. So if there's any failure, we have contingencies for that. And if it passes the autonomous testing phase, then we begin on-orbit operations, which will basically be taking pictures of targeted wildfire hotspot areas, transforming those pictures into Fourier transforms so that we can then send them down on the Earth if the Fourier transform graph is different than the typical Fourier transform graph. And a Fourier transform graph is basically just a graph showing which wavelengths, which colors are most present in an image. And this can help us because if there's a Fourier transfer graph, a Fourier transform graph that is typical to a location, for example, a forest might peak at the green wavelength because the forest is green. And if we detect a change in that graph, then we will know that there might be a wildfire or something that may not be supposed to be happening going on over there, and we can send it down to Earth. Because if we just send every picture down to Earth, we have thousands and thousands of pictures that we're taking that will take up a lot of data.
Our CubeSat consists of 7 subsystems: the structure, power, orientation, imaging, command, communications, and temperature subsystem. The structure subsystem holds the CubeSat together. The power system includes a solar panel and battery. In case of the battery failing, the solar panel will switch to directly powering the Raspberry Pi. The orientation subsystem will use an onboard IMU and reaction wheel to help the CubeSat orient itself towards a target. The imaging subsystem uses an onboard camera to take pictures of the forest fire. The command system, which includes the Raspberry Pi, processes the information received from the camera and communication subsystem. The communications system receives commands and sends images to the ground station. The temperature subsystem helps maintain an appropriate temperature for sensitive components like the command subsystem.
Here's our software architecture. Our software architecture is split into various subsystems in which we have one master control. There are various subsystems, physical subsystems such as the camera and the power supply located on the bottom of the software architecture, and then there is software-specific scripts such as failure contingency scripts, autonomous testing, built-in tests, debuggers, and backups. And our software architecture, our software is actually responsible for controlling the spacecraft using the Raspberry Pi to send out commands to subsystems and to manage failures, etc., etc. And we have three different modes that the software is in charge of. One of them is the active mode, in which the software turns on all of the subsystems, physical and software. And then we also have our safe mode, which is just which happens in the case of a failure. We go into safe mode, and this safe mode basically just turns on the master control and the communication systems. And then our navigation mode, which takes place when the satellite is in orbit, turns on the IMU, um, the rotation wheel, and other systems needed for the satellite to properly navigate itself pointed towards the Earth.
We used Onshape to model our CubeSat. We created an individual CAD model for each part used, attaching them into one large CAD model. We then used the model as a diagram for the physical build. Several challenges that we encountered with building the CubeSat include the laser cut holes not always fitting the screws, and the parts not aligning correctly. Additionally, we encountered issues when trying to connect the solar panel to the Raspberry Pi.
Here we have a list of all of the subsystems that will consume power during each mode. So we have three modes. We have safe mode, which is just the Raspberry Pi and communications. And here is the values for them, and how much power they consume, and how much power the battery can supply, and how much power the solar panels can supply. And we also have that for navigation mode, except now we've added things like the IMU and the reaction control wheel. And we also have the start mode, which is just all the subsystems in general.
Our CubeSat used a variety of materials, including acrylic panels, PCBs, solar panels, and various aluminum brackets. The total weight of our CubeSat is 471.22 grams.
Here's our link budget. Our link budget shows the amount of signal power that each system receives, such as the CubeSat and the ground station. So we have a signal to noise ratio, which basically depicts how much of the power that was stemmed from the transmitter is received, is heard, and surpasses all the noise that is around it. Here is our data budget. Essentially, our data budget tells us how much space each picture takes, how much space the software takes, and how much space everything, basically all the things saved on the SD card of the Raspberry Pi, how much that takes. And our budget actually is around 2 gigabytes is a great budget for we want to keep our data consumption under 2 gigabytes, and we are right at 1.876 gigabytes because we clear our imaging graph data every 12 hours. And here is our integration plan. Basically, all the parts are compatible with each other, such as the screws and the structural parts, And the devices also are plugged into the Raspberry Pi using GPIO pins and cords that we have pre-planned, such as the IMU. And the software is designed to be compatible with the devices and the Raspberry Pi. So that's great because we can control many of the devices on the Raspberry Pi using the software. And the structure is also designed to be compatible with the CubeSat's instruments, which is also great because the specific design for the structure was chosen by us so that we could put all the devices in the right spot and have it make sense from a mission perspective.
Prior to completing its flyover test, the CubeSat will complete a software test and a communications test. The software test will include camera testing. The CubeSat will use its camera to take a test picture of the environment. During the communications test, the CubeSat will send the picture it took of its environment to a ground station. The purpose of the flyover test is to simulate what would be like for the CubeSat to fly over a forest fire. During the flyover test, one person will pull the CubeSat over the grassy area. The CubeSat will take pictures over the fire and then send the pictures to a ground station. Moment of truth.
Okay.
Will it follow chatter or?
Go ahead. Okay.